Hey Precalculus, so we're going to be taking a look at vectors from here on out in chapter 8, and we'll sort of see how they're related to polar coordinates. They're actually very closely related. But first we need to just sort of understand what vectors are and sort of how they work on a basic level. So for instance, you might see the directions, sketch the vector, and write it in component form. Now you are probably going to see a problem like they would tell you P is at like 2, 3. And Q is at 4, I don't know, negative 1. Okay. If you see something like this, you're going to graph both the points. So I would go over 2, I would go up 1, 2, 3, and there would be my point P. And then for Q, I would go out 4, 1, 2, 3, 4, and down 1. There's my Q. And the vector is actually a line that goes from P to Q. And we put an arrow to determine the direction so that you know that you started at P, that it was the initial point, and that Q was the terminal point. So now to write this in component form, what we would do is figure out how far did we go over and how far did we go down. And you know, if you have nice graph paper and you drew the picture accurately, you can just count. I went over 2. And I went down 1, 2, 3, 4, so that would be a negative 4. If you didn't have graph paper, or if you were dealing with numbers that were so big that you couldn't deal with them, then the component form of the vector, let's call this vector u, is x2 minus x1 and y2 minus y1. So you would, if you're going to do this algebraically or show your work, this would be your x1 and your y1. This would be your x2 and your y2. So I would do 4 minus 2 for my x's, negative 1 minus 3 for my y's, and then 4 minus 2 is 2, and negative 1 minus 3 is negative 4. And component form here just means using these like triangle brackets instead of using a parenthesis. So this means I went over 2 and down 4. Now, to put it in ij form, to write the same vector out in ij form, I would just say 2i minus 4j. So this one right here is ij form, and this guy right here is component. So component has the triangle brackets, ij form has the i's and j's. Now if they ask you to find the magnitude and the direction of a vector, we'll just do this for vector u. Okay. So vector u is 4. And now vectors, it doesn't really matter where the vector is sitting necessarily on space. Like I could take this arrow, and as long as I keep it the same length and pointing in the same direction, I could shift it however I want really. So I could move it here over 2 down 4. And so for the sake of convenience, most of the time what we do is shift it back down to 0, 0, so that it's starting at 0, 0. So what this graph 2, negative 4 would look like if I moved it back to the origin is I would go over 2 and down 1, 2, 3, 4. So over 2, down 4, and then there's my vector. Okay. So now the magnitude of a vector. That word just means the length of the vector. It just means find how long this arrow is. And there is a formula for magnitude. By the way, the magnitude, the way that you would write that out with notation is the absolute value of u, but you read it as the magnitude. The formula for that, the magnitude of u, is the square root of x2 minus x1 squared plus y2 minus y1 squared. And that should look familiar to you. It's just the distance formula. So we could work this out with the distance formula. You could also just think of the Pythagorean theorem here. So I'm going to do the magnitude of u is the square root of, well, I know a squared plus b squared equals c squared, so 2 squared plus negative 4 squared. Let's see, 2 squared is 4, 4 squared is 16, so this is root 20, which simplifies down to 2 root 5. Because the square root of 4 is 2, and 4 times 5, yep. So this square goes down to 2 root 5. So there's the magnitude of the vector, the magnitude of u right there. And then the direction is just the angle that we've gone through. So I want to find out what angle is in the triangle here. Now, man, this looks really close to a 30, 60, 90. But I'm not 100% sure if it is, so I'm going to double check. I have opposite and I have adjacent, so that tells me TOA, tangent. So I would say the tangent of theta equals the opposite over the adjacent. And then to get rid of tangent, I would tan inverse both sides, or arctan. And so for my direction, when I do the inverse tangent, I get, let's see here, do they have arctan? Oh shoot, I don't have a calculator on this. I'm Googling it right now because my graphing calculator got swiped. So let's see, arctan of -2, because 4 divided by 2 is -2. And it gave it to me in radians, but I want it in degrees. There we go. So it gave it to me as 63, good old Google, for 63.4 degrees. And since it's going into quadrant 4, I know that's going to be a negative 63.4 degrees. So that would be the direction that my vector is going in, and this is the length or the magnitude. Let's see, what else can we do with vectors? Well, it turns out we can add them, and we can also scale them. So, for example, if I had some vector v, and I said it was 3, 1, so over 3 and up 1, and I'm still using my vector u from before, so it was over 2 and down 4, I can add my vectors together. So if I said u plus v, I would have 2, -4, plus 3, 1. And then you just add the components. So I'm going to add the x's, 2 plus 3, and that's going to give me 5. And I can add the y's, -4 plus 1, and that's going to give me -3. I can do this algebraically. I can also do it with a picture. So if I were to do this pictorially, I would have the vector over 3, 1, 2, 3, up 1. There's my vector v. And I would have, from the end of vector v, since I'm adding u to it, I would go over 2 and down 4. So from this vector, I'm going to go over 2 and down 1, 2, 3, 4, right here. So there's my vector u, because remember you can move u around on your paper. And the resultant vector is my answer. So notice that this vector right here, that arrow from the beginning to the end, is over 1, 2, 3, 4, 5, just like the algebra showed me, and down 1, 2, 3, just like it showed me. Okay. I can also, what we call scale, this 2 is a scalar, basically meaning that I am changing the size of the vector. And so if I want to scale u, I would do 2 times the vector u, which was 2, -4 for us. And you just scale both the x and the y equally. So I'm going to multiply both the x and the y by 2. 2 times 2 and 2 times the -4. So then I would get this vector 4 and -8. And so graphically, if I were to look at what that would do to the picture, the original vector u was over 2 and down 1, 2, 3, 4. So there's my original vector u. And when I multiplied it by 2, then I got over 4 down 8. So I would go over 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6, 7, 8. And notice it's the same direction, it just made the vector twice as long. It made the arrow twice as long. Let's see, what else can we do with vectors? Or what other types of problems might? Well, it might say the magnitude and direction are given, write the vector in component form. If you see a problem like this, they're going to give you something like the magnitude of u equals 5, and they're going to tell you something like theta equals, I don't know, like 2 pi over 3. Now, this is a lot like, if we're going to use little thought bubbles over here, r being 5 and theta being 2 pi over 3. This is how it sort of comes to play that vectors are a lot like polar coordinates, because what we figure out this vector is we're going to rotate 2 pi over 3. We're going to go out 5. And then to put it in component form, what we really want to know is how far did we go back and how far did we go up. You would say the vector u is magnitude of u times cosine of the angle, just like before we were doing r cosine theta for our x. And the magnitude of u times sine of theta, just like r sine theta. Okay. So I would have 5 cosine of 2 pi over 3 and 5 sine of 2 pi over 3. And then I've got to think on the unit circle, pi over 3 is in quadrant 2. It's where I've gone back a half and up root 3 over 2, because I haven't gone back as much as I've gone up. 5 and 5 times root 3 over 2. So in component form, my vector would be negative 5 halves and 5 root 3 over 2. And what that means is that I've gone back 5 over 2 and I've gone up 5 root 3 over 2 for my vector right here, my vector u. I guess I should put an arrow on it to make it vector. Very, very similar though to what we've been doing with polar coordinates. Last but not least, putting a problem like in a real world situation, because frankly, that's why we care. You're going to have a problem where, let's say it's an airplane, or maybe it's a person swimming in a lake, or basically a force acting on another thing. So in this case, the airplane heading due north at 300 miles an hour. So if I were to draw a picture of this, here's due north, and it's going 300 miles an hour, and so that means the length of the vector is 300 miles. So if I were to write the airplane, which I'm going to use J for jet, it's gone over 0 and up 300. And then the magnitude of J right now is 300. And then this airplane is experiencing a 40 mile per hour crosswind that's flowing in the direction north 30 degrees east. And so what that means is there's a wind blowing north 30 degrees east. And that wind, since it's coming from behind the airplane, it's going to make the airplane go faster, and it's also going to bump the airplane off course just a little bit. So what that would look like is we would have this little wind vector coming off at a 30-degree angle, and its magnitude, I'm going to use W for the wind, is 40 because it's 40 miles per hour. So the speed there is representing the length of the arrow. And when I put those two vectors together, what I'm going to get is the true vector that represents the airplane. Because the airplane's really going to move a little faster because of the wind, and it's going to get bumped off course just a little bit. And so when it says find the true speed and direction of the airplane, what they really want is the length of this resultant vector, and then what direction did it get bumped off by. So to find that, first I need to write the wind vector in component form. So let's see, if it's bumped off by 30 degrees north 30 degrees east, that means the actual angle that we're going to use for this guy is theta equals 60 degrees, because we have to measure from the x-axis. And so if I want to do this in component form, I would say W equals 40 cosine 60 degrees and 40 sine 60 degrees. That would give me W equals, let's see, cosine of 60 is a half, so 40 times that would give me 20, and then this would be 20 root 3 when I worked it out using my unit circle. And now this vector right here, the blue vector, is J plus W. So I've got J plus W equals, let's see, 0 plus 20 is 20. 300 plus 20 square roots of 3. Oops. Plus 20 root 3. Okay. So now I've got my vector for this. I could turn these into decimals, and that would probably be helpful. I think 300 plus 20 square roots of 3 is 334.6. And then from here, in order to find the true speed, of the airplane. I want to find the magnitude of J plus W. So I want to figure out how far did it go over, how far did it go up, and I'm going to use the Pythagorean theorem to find its length. That's going to be the true speed in miles per hour. And if I want to find the true direction of the airplane, then I want to figure out what this theta is, figure out what direction it's bumped off by, and then I'm going to give my answer as a bearing. So whatever this comes out to be, whatever this theta is, I'm going to say north so many degrees to the east, and I'm going to take this answer away from 90. I'm going to go ahead and let you guys finish out these notes. I'm going to have you find the true speed and the true direction of this airplane, and then you can check your answers in the textbook. In the textbook, this is technically example 6. So go ahead, try and do this on your own, and then when you do, look at example 6 and see if you were able to get the right answer. All right, that's it for tonight. I will see you guys in class.